Bismillahirrahmanirrahim. Welcome to the new lecture of Discrete Mathematics. Today we are going to study about Introduction to Tree Theory. So as we discussed in the last class about a graph, so tree is also like a branch of a graph, but tree have their own cases. So how we can say that this graph is a tree or this graph is not a tree. So coming to a definition of a tree, like we can say a graph T which include vertices and edges. So a graph T is called a tree. A graph T is called a tree if T is connected and has no cycle. Let's see, we have a this kind of vertices and all these vertices are connected now. So when this is connected, it means this is called tree. But if we just connect this with this, okay, so this will not a tree. This will be a graph, but this will not a tree. How? Because once you are starting from this point, you can come here, and you back to there. You back to on a starting point. So it's just like a cycle. So when it's a cycle, so it will not be tree. So for a tree, the reason is that all the point will be connected with each other but has no cycle. There will be no cycle. Now you can see all the point are connected with each other, all the point are connected, but it cannot make a cycle. If we can connect these two nodes, okay, these two vertices, so it will be loop now. So it will be loop, it will be a cycle. So when there is a cycle, it will not be a tree. But if there is no cycle, so it is a tree. Okay, so this is about tree. But now there is one thing more. If T is disconnected, then it is a forest. Disconnect means, let's say you have a vertices and these vertices are connected and this is not connected now, and this two is not connected, so this is called forest. So you have a lot of vertices and some of it is connected, some of not is connected, so we can say this is called forest. So let's come to the theorem of a tree. So if A, B are a unique vertices in a T or a tree, then there is a unique path. So what does it mean? Let's see, we have a A here and we have a B here. So we have a unique A and B vertices and you need to have a unique path. Let's see, this is our starting point. So once we need to move from A to B, so we will have a unique path. So if you can see this is called a unique path. Or we are moved from B to A. If we move to B to A, so this kind of unique path. So it's a theorem. So we can say that we have a nodes, we have all nodes, and we just select a point. This is point A, this is point B, or we can say this is vertex A, this is vertex B. So when we are moving from A to B, so we need to move by this point, by this way. Why? If we can move here then here, so we don't have another path now, so we need to come back. So no need to be repeat the vertex as I told you in a graph. So no need to be repeat. If you can move here and then here, again it will be repetition, so no need to use this kind of path. If you can use this, so no need to use this kind of path. Okay, so our basic path is move from A to B like this and move from B to A like this. So this is unique path now. So this is a theorem where we need to have a unique vertices, where we need to have unique path for vertices. So now I will show you another example where we can be decide that it is a tree or it is not a tree. Let's see, come to this one. Like theorem, again the same theorem, but we are saying that in theorem that we have A, we are moving from A to B, but between A and B we have some other vertices, vertex X, and or we can say from again maybe same thing, like we are moving from A to B and we have some other vertices and we can call it x or y. Okay, so once one object is moving from vertex A to vertex B, and there are some other vertices and edges, etc. So like this x and y we have. So maybe once it make a loop, then we can say that it's not a tree, because when it's not a tree, it means it will not have a unique path. Once you have kind of a loop like this you have a loop, so it means you have a multiple, like it's connected like this, connected like this, or connected like this. So it means it have a multiple of a path, that once object is moving from point A to point B, it will have a multiple path. When there's a multiple, it means there's not a unique path. Once there's not a unique path, so we will say that it's not a tree. Okay, so now it's a supposition, and we can say that this vertices and edges have a loop, so it's not a tree. Okay, so this kind of imagination that you can be make in your mind, and then apply on your graph, that this graph is a tree or not. So now coming to the another theorem, like if we can say in every tree and it is equal to vertices and edges, so we always use this formula. Keep in mind that edges is always one less than vertices. Okay, so what does it mean? Let's say you have 3 vertices, 1 2 3. So how many edges you will have? 2. You will have 2 edges. Okay, so edges will always one less than vertices. So we are going to apply 2 different cases. The case 1, that induction, we can say it induction hypothesis. So induction on edges, so base once edges is 0 and once edges is greater or equal to 0 or greater or equal to 1. Okay, so we are making some hypothesis now. So now let's come to the point. Let's see, we have a 3 vertices. Once we have 3 vertices, so how many edges we will have? 2, because it's based on formula for tree only. Because I mentioned this concept in a graph as well, but that concept is only applicable on a tree, not on a graph. Okay, but tree is a kind of a branch of a graph, I told you before. Okay, so let's come to the this case 1. In the first case, he's saying that once edges is 0, so we need to prove. So what does it mean? It means we have just only one vertex. So edges is 0, it means how many vertices we have? 1. 1 minus 1 is 0, so 0 is equal to 0. It's a proof. Simple. Okay, let's come to the second case. In the second case, they are saying that edges is greater or equal to 1. It means we need to have at least one edge. So it means how many vertices we need to have for our edge? So we need to have 2 vertices. So 2 vertices can make one edge. But there is one thing more. If I can get, or if I have one vertex, so from one vertex I can make one edge as well. But once I can make it like this, so it will be like a loop. Once it loops, so it will not be a tree. So it's not to be a tree now. So this is okay. So for that purpose, once we need to have one edge. So for one edge we need to have 2 vertices. Okay, so let's come to prove it out. Once we are saying that the same formula as I mentioned before, that we have a old tree. Let's say this is your old tree, and we need to make a new tree. So we can say that new tree at t prime is equal to t old minus v old. T is a tree and v is your vertex. This is kind of hypothesis you are making, and we can also be used like this as well, that that edges, new edges are e prime is equal to e minus 1. We can also be used like that, that vertices v prime is equal to v minus 1. It's kind of hypothesis. And we can also make that e prime, this is your formula, e prime is equal to v prime minus 1, because from a formula as I show you before. So now what's going to do, what we did, we made a new vertices and we made a new edges. So for this and for this we need to be find these value first. So that's kind of hypothesis. Okay, so this is called induction hypothesis. So now you can put value here and you can put value here, and then you can get the result. So once you are putting all these values, right here, E is equal to v minus 1. Okay, so as e minus 1, so e prime is equal, so e will be e prime plus 1, and for a v we need to find a v, so v prime plus 1 and minus will be here. So just simplify it, plus your result will be this. So it's a proof. Now whatever we told you here, so we prove it by using these hypotheses and put in this formula, and we got our conclusion. So this is your result. So you need to be keep in mind that once you are going to find out the induction hypothesis, so you can be use your concept to suppose some factor and prove it out. So we have a 2 3 t1 and t2 have a 2 3, and e1 is equal to 17 and v2 is equal to 2. E1 is known, so we need to find out v1, v2 and e2. So according to the formula as we have, so we have this formula. So put out the value of e1, and e1 is 17. So what will be the v1 now? v1 will be 18. So it will be 18. Okay, so how much will be the v2 now? So v2 is equal to 2 v1 and v1 is equal to 18. So v2 is equal to 2 v1, v1 is 18 multiply with 2, so 36. So how much your v2 is? v2 is 36 now. So now coming to e2, so again use your formula. You have this formula, put v2 is equal to 36 minus 1 and e2 is equal to 35. So this is your formula and method how you can find out v1, v2 and e2 from 2 3 4 or 5 trees. So you guys just see here that we have a 2 tree. Maybe I will give you an exam 2 3 4 5 10 11 number of trees, and I will tell you that find out v10 v5 and so on. Okay, so just keep in mind this is the way how you can solve your question, and how you can solve your tree is based on tree. So how you can solve that tree. So now coming to another example, and example is like about a graph. So give a graph G is equal to vertices and edges, where vertices is equal to edges plus 1 is based on this formula, but G is not a tree. What he's saying that G is not a tree. So now we need to find that this G is not a tree, but this formula is using here. So how we can prove that V is equal to E plus 1, which is the formula of a tree, but on the same time the graph is not a tree. So I'm telling you how we can prove this. So let's see. Once according to this formula, if I can tell you that we have a 3 vertices, so once we have a 3 vertices, how many edges we have? 2. Okay, so 3 vertices, 1 2 3. How many vertices? 1 2 3 vertices. Okay, but if I'm telling you what's about a tree condition. Tree is just like this. Once it is connected and cannot make a loop, it's a tree. But if I can But if I can make it like this, that we have a three vertices and two edges. This is edge 1 and this is edge 2. So now in this case we have a three vertices, two edges. This formula is satisfied, but this graph is making a loop, so due to making a loop, so it's not a tree. Simple method, simple way. Okay, we can also be like this as well, that we have a three vertices, okay, and it make a two edges. How many edges? It's edge 1 and this is edge 2. So once we have a three vertices and two edges, but due to these two edges it's make a loop, so due to making a loop it's not a tree. So this is a simple method. Once you can see this kind of a question in a book or in exam, so you need to be explained that this kind of a question 2 to 3 or 4 method, that if you can make like this, if you can make like this, if you can make like this, so it will not be a tree. Okay, so I can show you, this is if you can see this example, we have three vertices and two edges. If you can see this, we have a three vertices and two edges, but it's not a tree. Okay, so in this case, if you have a three vertices, vertex 1 2 3, and this is connected like this, so we can say it's a tree. But one thing keep in mind, that the tree will satisfy this equation first, but also satisfied in a graph that there will be no repetition, there will be no cycle. Once there is no cycle and this formula is satisfied, so the conclusion will be that it's a tree. Okay, so it was your lecture. Just watch it out. If you have any questions, just raise it in your comments, and hope it will find you well. So thank you for your time. See you in a next lecture.